Hello, welcome to part two of this three-part series on adaptive immunity. With this chapter, we're looking at specific immunity, in other words. Um, if you didn't realize it, I also have a posted three-part series on non-specific immunity or innate immunity as well. So these two chapters, they cover the immune system, general introduction to both sides of the immune system, the non-specific side and, in this particular chapter, the specific side. Again, this is part two, so we're picking up right in the middle of the chapter here, and we'll be discussing a few more topics, and then I'll end part two, and then there will be a part three to finish out the chapter. So let's get started. We're going to look here particularly at antibody structure, or antibody anatomy, I guess you could say. So with the structure of the antibody, this is very generalized, and this is a symbol that is used for the antibody. You can see there on the right-hand side of this picture. That is the antibody symbol. What does it look like up close? Well, there are two heavy chains, as you can see in the picture on the left, where the greenish colored longer chains of the antibody, they're called the heavy chains. And then you have what are called, colored blue, the light chains. And so these two areas, or these two chains, I guess I should say, are held together by disulfide bonds that are holding these proteins together, as sulfur is used in holding together many proteins, enabling them to take on different levels of structure in terms of proteins and their more complex structures. So sulfur is necessary to hold them together. And if you look at the close-up in the middle there, the enlarged antigen binding site to an antigenic determinant, or an epitope, which we had talked about in part one, you can see how the epitope goes into the antigen binding site. And the fit is very much kind of like in the case of an enzyme with its substrate, for example. We have an induced fit that's going on here between the epitope and the antigen binding site, and it's a highly specific fit between the two. And the Y shape is flexible at the hinge region. And so you can see in that picture there on the left, the hinge region where the two sulfurs are, that enables the antibody to assume the shape of a T. So it has some flexibility at this hinge region, hence the name hinge for it. And so these can move, and this enables them to latch on to other epitopes, and it gives them some flexibility so that they're not bound in a fixed shape. They actually have some flexibility to their shape as well. So anyway, the middle picture I wanted to point out there is, again, that the high level and high degree of specificity between an antigen, in this case the epitope specifically, and the antibody itself. And so that region is where the epitope will bind to the antibody in a very specific relationship. So we're going to look at the 5 different classes of antibodies, and this is just basically a survey of them. There's not a whole lot of in-depth discussion about them, and just where they are and their percentages and what their functions are. So IgG is monomer, so it's made of just one unit, and it's 80% of serum antibodies. So most of the antibodies that are flying around in our serum are IgG. They easily will migrate from blood to regions of inflammation, and so they're highly involved in the inflammatory response. We find it in blood and lymph, in colostrum, and in intestines as well, within the Peyer's patches, for example. They're able to cross the placenta, so the IgG antibodies can be transferred from mother to fetus via the placenta, which is helpful, obviously, for the developing baby. They enhance phagocytosis through opsonization, which we'll talk about later in this segment. They neutralize toxins and viruses. They activate complement. And because of this transplacental transfer, they're able to protect the fetus and the newborn. And they're the longest surviving antibody. Out of the 5 different classes of antibodies, IgG are the longest surviving ones. IgM antibodies are pentamer, meaning so pentagonal. They've got 5 monomers that are held together by disulfide bonds. 5 to 10% of serum antibodies, they're the predominant one responding to the blood type ABO antigens. And so this leads to what they do is they agglutinate. Because of their large size and they have these 10 points of contact where they can bind with all of these numerous different epitopes just on one unit of an IgM. We find it in our blood, lymph, colostrum as well, and on B cells too. So these get transferred from a mother who is able to nurse her child, being transferred from the mother to the child, and then conferring a little bit of immunity for the child. Now, this does not create lifelong immunity, but with a newborn, this helps the newborn as its immune system is maturing during those first few crucial months of life when the immune system is developing within the newborn. Because of their pentamer size, their large size, they cannot leave the blood, and so they remain within the circulation, and they are the first antibody produced in response to infection, and so that makes these a diagnostic tool. So you can see that they're in the early stages of an infection because the IgM numbers spike, and so you see many of them. If you were to do a titer, you would see loads of IgMs. They enhance phagocytosis as well. So they will agglutinate antigens, and then as a result of that, phagocytosis becomes enhanced, more efficient, because there are fewer antigenic units, so to speak, for the macrophage to deal with and phagocytize. IgA antibodies, they are dimer. They're made of 2 subunits. Overall, in the body, they're the most abundant antibody. In our serum, about 10 to 15%. So a little bit more than the percentage of IgM antibodies. They're the most common antibody in our bodily secretions, in mucus, saliva, tears, and milk that is produced. Their main function is to prevent pathogens from attaching to mucosa, otherwise known as neutralization, especially intestinal and respiratory pathogens. And so where we have an enormous amount of mucous membranes, IgA antibodies are there to prevent the pathogens from adhering to those cells, then adhering to each other then as a result of that as well, and then creating a biofilm, which then leads to all sorts of problems for the host as a result of that. So if we can stop their ability to adhere to the mucous membranes and to each other, we then inhibit their ability to form biofilms, which then greatly reduces their toxigenicity and their virulence, and so they don't become, they're not nearly as pathogenic then as a result of this neutralization. IgD antibodies are monomer as well, like IgG. They compose a very small number of serum antibodies, 0.2%. We find it in our blood, in our lymph, and on our B cells, and they initiate the immune response on B cells. So these would be, remember, they're immunoglobulins, and so some of them remain attached to the B cell plasma membrane, and so they can initiate the immune response within the B cell and begin the process of, say, clonal selection, for example. They may destroy, and I use the word may because there's still some things to learn about IgD. They're a bit enigmatic. They may destroy B cells that produce antibodies against host tissue. So whenever we start developing autoimmune issues, it looks like in some research it has shown that IgD destroys these B cells that are producing antibodies against our own tissue, causing them to undergo apoptosis. But not always. Some research has shown it, and some research has not shown that to be true. So there's still more to be learned about IgD. They're a mystery. IgE antibodies, those are monomers as well, 1 unit, and they make, and that is not a typo, an even smaller amount, way smaller amount. Let's see, that's tens, 100,000, 10,000, 2/10,000ths of a percent of serum antibodies, an incredibly small number of them. So very, very few IgE antibodies. We have them on mast cells and basophils. When you see mast cells and basophils, you think, what response? Yes, the immune response. And so these guys are involved in not the immune response, forgive me, the inflammatory, I knew it started with an I, the inflammatory response. And so these guys are involved in the inflammatory response and allergic reactions. They're in our blood, skin, and mucous membranes. They initiate allergic reactions, which leads to complement. The complement proteins in the system of these proteins that are complementing the immune system, phagocytic cells as well, and lysis of parasitic worms. So if you have a parasitic worm infection, your IgE antibody count is going to be quite high as a result of that. So I don't know if you're infected with a parasitic worm or not, but if you are, you will have a high level of IgE because their concentration greatly increases during parasitic infections and allergic reactions as well, so that makes them diagnostically useful. They are the shortest surviving antibody, but when they are present, they lead to a whole heap of trouble for parasitic worms if you happen to have a parasitic worm infection. And of course, not always. I mean, some parasitic worm infections, they're with us for quite a long time. But in many instances, the IgEs will lead to the destruction of the parasite. So those are the five classes of antibodies, specifically the immunoglobulins. Those, a couple more terms here. Antigen antibody complex. It's kind of like the enzyme substrate complex that you may have heard of before. An antibody bound with its specific antigen. And so we have similarities here. So it's not just, the enzyme is not the lock and key, the induced fit, the hand and glove, whatever you want. It's not the only one that has that kind of, that exhibits this kind of binding, but antigens and antibodies do as well. Affinity is the strength of the bond between an antigen and an antibody. So there are some cases where the affinity is very strong and the antigen cannot release itself from the antibody. And for us, that's good. Sometimes the strength of the bond is weak. And so as a result of that, the antigen gets released from the antibody. The chemical bond is not that strong. And so now the antigen is not tagged for destruction, the bacterial cell or the virus or whatever it happens to be. So affinity does play a major role in our ability to ward off these infections. The antigen-antibody complex tags foreign cells for destruction by phagocytes, like I mentioned before. And again, it's not the antibody that's doing the destruction, it's the phagocytes. That's what they're designed to do. Just let them eat. But they have to receive a signal to do that. And what signal is sent to them? A whole bunch of signals. But in this case, it's the antibodies, which can initiate a whole other host of signals for the phagocytes to come and eat. Specificity, we've talked about this a lot within this chapter. Antibodies can distinguish between extremely minor differences in the structure of two different antigens. Therefore, antibodies can be used diagnostically because they are so highly specific. And so that's why we do antibody titers. And so we look for the count. And we know what the major functions are of the different classes of immunoglobulins. And so therefore, we can use them, once we know what the count is, diagnostically, which then can lead to proper treatment and so on. These are the major results of what's called antigen-antibody binding. And so I have it in pictorial form here, and then I have explanation in a couple of slides for each of these. So agglutination, clumping them up in the upper left, reduces the number of infectious units to be dealt with. And so what these antibodies will do is join to a number of infectious units, the terms used here, antigens, epitopes, whatever you want to call it. It clumps them up and puts them into bunches so that the phagocytes can carry out phagocytosis more efficiently. So there are fewer antigenic units for the phagocytes to deal with, have to go hunt down and consume. Opsonization, this enhances phagocytosis. So the antibodies coat the antigen. And the example that they're showing here will be a bacterial cell. So you can imagine with all these antibodies on it, I don't know, we could say it tastes better with these antibodies on it to the phagocyte. And so it will consume them, and it will consume them rapidly and efficiently. So that's about the only analogy I can think of that would kind of go with this, is that it makes the antigen just taste better to phagocytes. And so they love to eat. And so if it tastes better, they're going to eat more of them. Neutralization. So what happens here is that it's going to block adhesion. And so you see the different examples that they give. Block adhesion of a virus, so it can't enter a cell, which is, of course, what it has to do. They're obligate intracellular parasites, and so they have to get into a cell. It'll neutralize bacteria so that they don't form biofilms. And if they can't form biofilms, then their pathogenicity goes way down. And it also can block the attachment of toxins so that the toxin cannot enter a cell and then cause the damage, whatever it happens to do within the cell. Like you block the tetanus toxin from getting into muscle cells, and then they can't cause the signs and symptoms of tetanus, the uncontrollable contractions. The next one going up, antibodies attached to target cell cause destruction by macrophages, eosinophils, and our favorite cell, the natural killer cell. And so what is this called? It's a mouthful. Antibody-dependent, cell-mediated cytotoxicity. And so what happens here is you've got, in this example, they have a large target cell, and they're saying, I guess, a parasitic worm. And all over its surface are going to be epitopes. Well, the antibodies will attach to the epitopes. The antibodies then will cause will lead to the attraction and the attachment of white blood cells like eosinophils. Eosinophils then, through the process of this attachment, then will begin to release lytic enzymes and perforin to penetrate the membrane around the parasite. And so that will lead to its lysis. So if the eosinophil is not attached to the antibody, it's not going to release its lytic enzymes. But once it is, there's a cascade of events that takes place. The enzymes get released, and goodbye parasite. And then finally, at the upper right, activation of complement. And so what happens is some of these antibodies are working very closely and intimately with the complement proteins. And so once these antibodies stimulate the complement proteins to do their thing, and that first domino falls, and then again we have a cascade of events that leads to the membrane attack complex, which then leads to the lysis of the bacterial cells. So these are 5 different ways that antibodies and binding with their antigens, the interactions between the two, 5 different ways of what happens then to the antigens, how our body deals with these pathogens. This is just the mouthful one, antibody-dependent cell-mediated cytotoxicity, looking at it up close. So not only do eosinophils come in, but these antibodies will also attract, of course, macrophages, and then they will release cytokines and lytic enzymes, and then it's over for this large parasite. And you can see the micrograph on the left. This is a fluke. It's a parasitic worm, a helminth. It's not like, I'm not saying it's a mistake. Anyway, so this is a helminthic organism here called a fluke, and these are any eosinophils, and that's all that fuzzy stuff on the outside. That means damage is being done, and this is not a happy fluke, not at all. This is just what I talked about, but in text form. So these are the 5 results of antigen-antibody binding together. So this would be, if you want to make flashcards or something, that would be helpful here to look at this slide. Our last slide in part 2 here, this is self-tolerance. Can you tolerate yourself? Well, some of us have trouble tolerating ourselves, but that's a topic of psychology, not microbiology or immunology. What we're talking about here is, can you tolerate your own cells? So normally, our body doesn't make antibodies against our self-antigens. In other words, we don't make antibodies against our own cells or our own tissues. Normally, we don't. But if it does, we call that an autoimmune disease, auto meaning self. So it's a self-immune disease, such as Sjogren's syndrome, fibromyalgia, rheumatoid arthritis, lupus, type 1 diabetes, and so on. There are a number of autoimmune diseases out there, and these are all malfunctions in the immune system, where the antibodies, your immune system is making antibodies against your own cells and tissues. So we want to undergo, when this happens, we want to undergo clonal deletion, which we all do. But sometimes the clonal deletion process and system doesn't work. And so these B cells and T cells that are reacting to self-antigens do not get deleted. And so as a result of that, then autoimmune diseases can result. So what is clonal deletion? It's the process of destroying these rogue B and T cells that react to self-antigens. And it may be carried out by IgD antibodies. Remember how I said IgD? There's still things to learn about IgD. He's a mystery. It looks like IgD may carry this out through a series of regulatory processes that will lead to the deletion, not the selection of these cells, but the deletion of them and removing them so that autoimmune diseases do not form within a person. Well, that's it for part 2. Please tune back into part 3 if you'd like to see the conclusion of this chapter on specific immunity. And if you have not yet subscribed, please do so. And of course, share this video with others. I mean, this is free education. You don't have to pay for this. And I hope it's been useful education for you as well. So thank you for watching.